Physicists thought they'd solved the universe until a simple experiment with light and metal broke physics. By the end of the 1800s, there was this genuine belief among scientists that physics was basically finished. We had equations for motion, gravity, electricity, magnetism, and light. If you wanted to understand how the universe should work, well, classical physics had you covered. And then someone shone some light at a piece of metal. Not a complicated experiment. No particle accelerators, no billion-dollar machines, just light and metal. But what they saw made absolutely no sense. Shine a bright light at the metal, nothing happens. Dim a light, just a different colour, and suddenly electrons start flying off the metal. According to everything physicists believed at the time, this should not have happened. But that one failure didn't just break an experiment, it broke physics, because it forced us to abandon our understanding of what we thought light was and accidentally discovered quantum mechanics. To understand why this was such a disaster, you have to understand how confident physicists were back then. In the late 19th century, physics was built on an incredibly successful framework called classical physics. Newton's laws explained motion. Maxwell's equations unified electricity, magnetism, and light. Thermodynamics explained heat. The universe felt mechanical, predictable, complete. In fact, there's a famous quote often attributed to physicists of the era that all that remained was to measure things more precisely. But that confidence turned out to be wildly misplaced, because light, something they thought they understood better than anything else, refused to behave. So here's the setup. You take a clean piece of metal and you shine some light on it. You measure whether electrons are emitted from the metal. Classical physics makes a very clear prediction. Light is a wave, and the energy that a wave carries is determined by its intensity. So if you shine a brighter light, you deliver more energy. More energy should knock electrons loose. Dim light shouldn't do much, and bright light should rip electrons away from the metal. But when physicists actually did the experiment, that's not what happened. They increased the brightness of the light? Nothing. They increased it more? Still nothing. No electrons were being emitted from the metal. Then they changed one thing. They changed the color of the light. Suddenly, electrons flew off the metal immediately, even when the light was dim. This wasn't a minor discrepancy, this was a full-blown crisis. According to classical physics, bright light should always work. Color shouldn't matter. But the universe refused. Longer than a certain wavelength? Nothing happened, ever. But with colors below a certain wavelength, electrons are rejected immediately. No delay, no build-up, and no compromise. Physics had encountered a brick wall, and the worst part? The experiment was simple and repeatable and undeniable. There was no blaming bad equipment. You couldn't tweak the equations. Reality was very clearly saying that your model was a huge cock-up. This understandably caused some concern. But then in 1905, a renowned cousin marrier changed everything. Albert Einstein proposed something radical. What if light isn't just a wave? What if light comes in discrete packets of energy? Not smeared out, not continuous. Individual chunks. Each packet carries energy proportional to the light's frequency, its color. Low frequency light? Well, they're low energy packets. And high frequency light? High frequency packets. Here was the key insight. If a single packet of light doesn't have enough energy to free an electron, it doesn't matter how bright you make that light. It doesn't matter how many of those packets you shine at the metal. It will never cause an electron to be knocked away from the metal. But one single high frequency light packet? That's enough. And by the way, we now call those packets photons. This explained everything. Why brightness didn't matter, why color did, why electrons were emitted instantly. Each electron interacts with one photon. No sharing, no energy buildup, no delay. If the photon has enough energy, the electron escapes, and if it doesn't, then the electron remains in the metal. This phenomenon became known as the photoelectric effect, and if you studied physics till the end of high school, you've probably seen it on your desk. But it was the first clear experimental proof that energy is quantized. Reality wasn't smooth, it was granular. Something that surprises a lot of people is that Einstein didn't win his Nobel Prize for relativity. He won it for explaining the photoelectric effect. Because at the time, reality was controversial, but the photoelectric effect was undeniable proof. It was measurable and practical, and it was revolutionary. In fact, without this discovery, solar panels wouldn't exist. Digital cameras wouldn't exist. Modern technology is built on this broken experiment. So the photoelectric effect wasn't just about light, it shattered a worldview. Nature's probabilistic. Reality doesn't behave intuitively. And once you accept that, you open the door to quantum mechanics, wave-particle duality, uncertainty, superposition. Everything strange about modern physics traces back to moments like this. Physicists thought the universe was solved, but they were wrong. If you enjoy stories where physics breaks and has to rebuild itself from scratch, this channel is about the moments when the universe forces us to rethink everything. So please like the video and subscribe for more.